In this video, we continue with our study of thermochemistry and problem solving. And we're going to spend a little more time on calorimetry. Here are our basic equations that we remind ourselves on last time. Heat flow Q is equal to Cp delta T, or we can also express Q as mCp bar delta T. We looked at two types of calorimeters, the coffee cup type or the open calorimeter, which measures enthalpy, and the bomb calorimeter, which measures internal energy, that is delta E. The bomb calorimeter is unique in that inside it has a metal bomb. It's called a bomb. It's a metal container that seals very tightly, and the volume does not change during processes. You can have very energetic releases and the volume does not change. So if there's no volume change, there's no PV work. So in the case of delta E is equal to Q plus W, in this process, there's no work involved, only heat. And so the heat release that you measure here is delta E. Let's take a typical example. When a sample of an ultrafine powder of magnesium is an alkaline earth metal, actually burns quite violently, and that happened in one of the early spacecraft on the launch pad. If magnesium is combusted in a bomb calorimeter that is charged with excess oxygen, magnesium oxide is produced. If we have a sample that is 0.5756 grams of this ultrafine powder and we burn it, we see that the calorimeter that has a heat capacity of 5.718 kilojoules per Kelvin increases its temperature from 19.785 degrees Celsius to 22.302 Celsius. In this case, what is the change in internal energy for oxidation of magnesium to magnesium oxide in kilojoules per mole of magnesium? We can write the reaction out as such. Magnesium solid plus a half a mole of oxygen gas goes to magnesium oxide. In this case, it doesn't matter how we write out the reaction. This is an experimental study, and we have a given mass of magnesium. Our heat measured is simply based on the mass of magnesium, not how we write the reaction out. In this case, we want to know how much heat released per mole, so we need to convert our mass into moles. Our 0.5756 grams of magnesium divided by the atomic mass of magnesium gives us 2.3677 and some digits times 10 to the minus 2 moles of magnesium. So now we have the molar amount of magnesium. Let's turn to the heat release for this process. Q for our calorimeter is equal to the heat capacity of the calorimeter multiplied by the change in temperature. In this case, the temperature units, we didn't convert these to Kelvin since we're taking a temperature differential. If we were taking an absolute temperature, it would be an issue. In this case, it is not. So we take our heat capacity, 5.718 kilojoules per Kelvin, multiply by the temperature differential, and we see that the calorimeter absorbs 14.39 kilojoules during this process. So our system, the magnesium, which burns to form magnesium oxide, is releasing 14.39 kilojoules. Based on this, then, we can calculate our molar heat release. So here we have 14.39 kilojoules for 2.3677 by 10 to the minus 2 moles, or 607.9 kilojoules per mole. That number is fairly close to the enthalpy of formation of magnesium oxide, which it should be, as we would see from the reaction above. Next, we'll look at how we tie together stoichiometry with our thermochemistry. We can write out a thermochemical equation, which is a balanced reaction that also lists the delta H of reaction for the process. And we know the sign of delta H, as we saw in our last video, indicates whether the reaction is exothermic or endothermic. If delta H is negative, the reaction is exothermic. If delta H is positive, the reaction is endothermic. The magnitude of delta H is proportional to the amount of substance, and so it's important to recognize that the way we balance the equation will determine how the magnitude of delta H in a thermochemical equation. We will see this in a moment. It's important to include this. The value of delta H can be used in calculation in the same way as a mole ratio can be. And we'll see how we do this in just a moment. Here's our flow chart that we looked at in our concepts video. The amount of A can produce an amount of B, and we know that that balanced equation will tell us a molar ratio. The way we write that molar ratio then will determine how we write out our delta H of reaction equation, and our final value of heat absorbed or released will be based on that stoichiometric ratio. Here, these are the standard enthalpies which we'll be using for our process. In particular, in this case, we're going to be looking at methanol. That's under carbon. That's CH3OH. And we'll be looking at carbon dioxide and water in gaseous form under oxygen. So we'll need those. Here is the process that we are looking at. We have 0.5 liters of CH3OH. It's an organic compound known as methanol, sometimes called wood alcohol. It has a density of 0.792 grams per milliliter. Methanol burns. Sometimes that's used in little alcohol lamps. It's burned in excess oxygen to produce carbon dioxide and water. What is the enthalpy change for this process? That being burning of half a liter of methanol. We're not looking at the standard enthalpy now. We're looking at the overall enthalpy for our process. But for this, we will need to get the standard enthalpy. And to do this, we need to start off with a balanced chemical equation. Let's write things with whole number values like you did earlier when we were looking at stoichiometry in Chapter 3. Here we see 2 molecules of CH3OH react with 3 molecules of O2 to give 2 molecules of carbon dioxide and 4 molecules of water. And the water should be as gas. We've not written down all the phases on here. That will be important later on when we do the standard enthalpy. So we understand carbon dioxide is a gas and water is going to be as a gas. Methanol is a liquid. We need the standard enthalpy for a reaction to begin working on this. So the standard enthalpy of reaction is the standard enthalpy of the products minus the standard enthalpy of the reactants, as written for this stoichiometric form. So we'll write this out. We see 2 times the enthalpy of formation of carbon dioxide plus 4 times the enthalpy of formation of water vapor. That's our products enthalpy of formation. We subtract off the reactants. O2 is 0 as an element in its standard state. So we just take 2 times the enthalpy of formation of methanol. So then when we get the number here, we get minus 1,277 kilojoules. That is per 2 moles of methanol reacted. It's important to recognize this. If we burn 2 moles of methanol, we get 1,277 kilojoules. If you take only 1 mole of methanol, you'll get half as much energy released. Now we need to determine how much methanol is contained in a half a liter. So let's do this conversion. 0.5 liters of methanol is 500 milliliters of methanol. 500 milliliters of methanol times its density gives us the number of grams of methanol that we have, 396. And then the mass of methanol divided by its formula mass, which is 32.04 grams per mole, gives us 12.36 moles of methanol. Now we know that we get 1,277 kilojoules per 2 moles of methanol. How much heat do we get for 12 moles? We could set that up as proportionality. And here we see this as such. 1,277 kilojoules per 2 moles times 12.36 moles. Moles cancel out. We need to do 1,277 divided by 2 times 12.36, and you will get 7,890 kilojoules. This answer should have 3 significant figures, and that's what we have here in this answer. So this is not the standard enthalpy, of course. This is the enthalpy for burning a half a liter of methanol. That tells us the energy we should get out, and if you do the experiment correctly, you will see that you actually do get that amount of energy out from this process. Now we'll look at Hess's law. Hess's law can be stated as the enthalpy change of an overall process is the sum of the enthalpy changes of its individual steps. Delta H for an overall reaction calculated if the delta H values for the individual steps are known. We also said this in another thermodynamic phrase. The enthalpy change around a closed cycle is 0. H is a state function. But as we think about this, if we have a particular process we want to understand in terms of the enthalpy that occurs, but we don't have that value, if we have a series of steps that will ultimately produce that, then we can use those in combination to determine what the overall enthalpy is. So we're going to look at an example of a problem, and this problem can be kind of sliced up some different ways, but there are more complex problems that we'll come across later on, particularly when we come to lattice energies for ionic compounds, where Hess's law becomes very important in what we call a Born-Haber cycle. Hess's law is used very regularly in research and development when you're looking at new materials and determining enthalpies of processes. So let's take an example. This is a bit of a complex example. Given the following reaction data. So you see you've got 5 reactions here. The first one, nitric oxide plus nitrogen dioxide, gives us dinitrogen trioxide. Delta H of reaction is shown on the right-hand side, negative 39.8 kilojoules per mole. The second reaction, nitric oxide plus nitrogen dioxide plus molecular oxygen, gives us dinitrogen pentoxide. The third reaction, nitrogen dioxide, 2 molecules of that will react together to form dinitrogen tetroxide. Fourth reaction is 2 moles of nitric oxide or nitrogen monoxide. Reacts with molecular oxygen to give 2 moles of nitrogen dioxide. And finally, dinitrogen pentoxide solid can go to dinitrogen pentoxide gas. So the question we have is, what is the standard enthalpy for the following reaction? That is dinitrogen trioxide gas plus dinitrogen pentoxide solid, forming 2 moles of dinitrogen tetroxide gas. What is the enthalpy for that? What we can do is we can combine the upper 5 equations such that all of the reactants and products cancel in an appropriate manner to give us the bottom reaction. Then we can add the resultant to determine the enthalpy for the process. So here are our 5 reactions, and underneath is the reaction that we want to produce. If we simply add the top 5 reactions, we will not get the reaction on the bottom. Things will not appropriately cancel. You can prove this to yourself. Let's break this down into steps. Let's look first and say, okay, we start off with dinitrogen trioxide as a gas. Which step above can get us there? Well, we see the only reaction above, which includes dinitrogen trioxide, is number 1. And that has that as a product rather than a reactant. So we will reverse reaction number 1 because we need N2O3 as a reactant. And if we do that, we end up with N2O3 going to NO plus NO2. So if we reverse the reaction, what do we do with the delta H? We change the sign. Our second step, we need N2O5 solid as a reactant as well in our final equation. So we can take reaction 5 and we can use this straight up. N2O5, dinitrogen pentoxide solid, goes to dinitrogen pentoxide gas. The enthalpy of that process is 4.1 kilojoules per mole. The next step is we need 2 moles of dinitrogen tetroxide as a product. We can see that in our final resulting reaction. So we need N2O4. And where can we get that? Well, we see that reaction 3 will get us there. That has N2O4 as a product. So we can use reaction 3, but we need 2 moles of this because we need 2 moles of N2O4, and reaction 3 only has 1 mole of N2O4. So we multiply the entirety of reaction 3 by 2, and therefore the standard enthalpy for that process will be needed to multiply by 2 as well. So that gives us 114.4. That is 2 times 57, negative 57.2. So now we have our resulting reaction, at least all the necessary pieces. We have N2O3 and N2O5 as reactants, and we have 2 N2O4s as product. If we add all these together, we see that we have the underlying pieces are what we need. And then I've crossed out the excess NO2. So for example, we have 4 NO2s to start off with as a reactant and 1 NO2 as a product. So we cancel the product side and reduce 4 down to 3. But we're still not there. We have some extra compounds around and we need to eliminate those. So we'll need to bring in reactions 2 and 4 to complete this task. So here's our goal. N2O3 plus N2O5 going to 2 N2O4s. And this is where we left off on the last slide. So continuing now, we need to eliminate the NO2s, and we need to produce NO and N2O5 gas. So N2O5 gas is a product in number 5. That's where we got that. But we need to find another place where it is, and that's reaction 2. And so in reaction 2, we can reverse that one. And if we reverse that one, we can eliminate that N2O5. So we reverse reaction 2, and so we just take plus 112.5 for the enthalpy for that process. And then the last thing is we have NO2s and NOs that we need to eliminate. And so we're going to look to reaction 4 to do that. And reaction 4 directly eliminates all the rest. And so what we can do is we can combine everything that we've done thus far. So here we have this. We have reaction 1 reversed, reaction 5 straight up, reaction 3 times 2, reaction 2 reversed, and reaction 4. I've crossed out all the reagents which are equivalent on reactant and product side in total. So for example, there's 4 moles of nitrogen dioxide coming from the third line, and we have 2 moles of nitrogen dioxide coming from the last line, number 4, and then 1 mole coming from the second last line, that's number 2, and then from the first line, that's number 1. So those 4 NO2s will cancel with the 4 reactant NO2s in number 3. And if we do this for all the partners, we end up with N2O3 plus N2O5 goes to 2 N2O4. And we simply add up all the enthalpies as we have determined them for each of these new processes that we've combined together. And we end up with negative 22.2 kilojoules per mole. So this is a case where we had an enthalpy of reaction that we could not determine straight up based on the data that we had, so we had to use this in combination. And there are indeed many cases like this where we run into the need to use Hess's law. That concludes chapter 6. We'll next move on to chapter 7.